Alright, so welcome back. Now where we left off last video, we had covered a lot of the theoretics about the normal distribution. We're going to return to a couple of more theoretical points, but we're mostly going to be using these ideas of z-scores to talk about how we can apply this to compare across different kinds of measurements that may not always have the same scale. So, let's say that in this example we have a client who takes a depression inventory. We're going to say this is the BDI, the Beck's Depression Inventory, one of the most popular or most widely used depression inventories, that they have a score of 42 in that. Now, we know because research tells us that the population average for depression is 31 and the standard deviation is 5. The highest possible score is 100. So where does this fit into the rest of the population? Very important question, right? That you're a therapist, you give your client this inventory to see whether or not they have depression or whether or not their depression rates differ from the population. And you find they have a 42 compared to a 31. Your question now, what's up to you as the therapist, is to make a judgment based on your understanding of statistics. 31 and 42. Is this enough of a difference to raise any alarms? Is 42 significantly above 31 when you factor in the natural variability that occurs in a scale like this? We know that there's going to be people with different with different depression levels. The question then is 42 greatly above average? Is that greatly above, sorry, I hit the microphone. Is that greatly above other people's scores and averages? All right, so how do we do that? We're going to find the z-score for this. If we want to know how does this person fit into the rest of the population, we can find the z-score to find exactly how much above average a 42 is. So let's do that. So here is our z-score formula. So what we're going to do is we're going to put for x, we know that that's going to be 42. So that is our observation, that's our data point that we're comparing to the population. And we're going to plug in the population parameters now, that the mean is 31 and that the standard deviation is 5. So that is going to give me 42 minus 31, which is going to give me 11. And then we're going to divide that by 5, which means that z is going to be equal to 2.2. So anytime, and this is, I think this is good practice if you want to be like me, and I like to be careful with this stuff. Anytime I get a z-score like this, and this will be also handy in other chapters too, which is why I think it's a good practice to start doing this. I always think about placing that on the normal distribution. So I got a 2.2, which means that it's probably going to be somewhere close to like right here. 2.2, a z-score of a 2.2. In other words, that this value is going to be not only above average, above the mean, but 2.2 standard deviations above the mean. And if you think about the previous, previous video, I was talking about how in IQ, if you are above 2 standard deviations, that's pretty rare, right? That's a pretty rare value. It means that you're in the top 2.5%. And so what we're saying here is that this individual must be somewhere above the top 2.5% if they are getting a z-score of 2.2. So we can conclude that this client's depression score is much higher than the rest of the population. This is going to lead us to the last really big theoretical principle of normal distributions for this chapter, and that's called the empirical rule. The empirical rule is a good way of knowing just how rare or just how unusual a data point is if we know the population parameters. So 68% of all values are going to lie within 1 standard deviation of the mean. So in other words, if we were to plot out our distribution, this bell that I've already drawn like 6 times in the last 15 minutes, if I was going to draw that out, that 68% of the data are going to fall basically within this right here. Ooh, that was really bad art, and I cannot erase that. And then 95% of the data is going to fall within these boundaries, which is roughly about 2 standard deviations away. And so that is 68%, 95%, and then the more elusive 99.7% for even further out to these tails. So basically what all this means, and I'm sorry for the kind of crude drawing here, that basically most of the data are going to fit between the 1 standard deviation below and 1 standard deviation above the mean. In other words, 70 IQ to 130, 85 IQ to 115 IQ. 95% of the population is going to fall somewhere between -2 standard deviations and +2 standard deviations. In other words, 70 and 130, because we know standard deviation is 15 and the mean is 100. And that the vast majority, so 99.7% of the population, is going to fall between the -3 standard deviations and +3 standard deviations of the mean. In other words, to think about IQ, that would be 70 minus 15, so that's 55, and 145, so 130 plus 15. So most people are going to fit somewhere between 55 and 145 in their IQ. So what that would mean is that if somebody scores outside of that, outside of 3 standard deviations above or below, that is exceedingly rare, and usually that means that you might have an outlier on your hand. That if somebody has a value that is more than 3 standard deviations above or below, that's usually a red flag that something might be wrong with that individual's data. So this is also called the 65, 95, 99 rule. So it's just a quick and easy way to know where you are, or how rare your data, how unusual your data might be, depending on your standard deviation. If it's 1 standard deviation, then it's within 68%. If it's within 2 standard deviations, then it's within 95%. Anything above 95%, scientists are usually going to say that is exceedingly rare. Alright, and here's just a graphical representation, which is way better than the drawing that I had on the previous slide. But there you go. So that is what it looks like. Alright, how are we doing for time? We're doing okay. Alright. So, one of the final things that I want to do is compare this with other scores. So, a lot of times in psychology, we aren't going to know the center of a data set. And what I mean by that is, like, if I get like the BDI, which is for depression, and I get the BAI, which is for anxiety, they may not have the same population means. They may not have the same standard deviation for those scales. So it may be our job to try to understand if somebody gets some value on their BDI, on their Beck Depression Inventory, what will be the equivalent value of that on their anxiety scale. Another way to think about this would be like if you wanted to know, like if you took the SAT and you got pretty good on it and somebody asked what you made on the ACT and you don't know, but you wanted to find what the equivalent of that would be for the ACT, you can do that using some of the methods we're going to go over here. Basically, we want to find the z-score of our value. So if we're trying to compare it for the ACT, for example, we're going to take our SAT score, we're going to find the z-score for that SAT score, then we're going to multiply that z-score by the standard deviation of the ACT, so of our new scale, and then add that to the mean of the ACT. And that'll give us what our value of the ACT test would be if we had taken it, given what we know about SAT. And this is that formula that you're seeing here, where you're going to take the z-score for your data, you're going to multiply that by the standard deviation, then you're going to add all of that to the population mean, and that's going to give you your projected data observation. Sometimes you'll see this as x, sometimes you'll see it as x prime. The prime usually means predicted, so in this case we're trying to predict what that value would be. So here is an example that I spent way too long trying to find accurate parameters for this. So the Beck Anxiety Inventory and the Penn State Worry Questionnaire. Now, for all intents and purposes, most times when we mean anxiety, we also mean worrying, right? If somebody is highly anxious, that usually means that they worry a lot. So we're going to assume that these two scales have very similar psychometric properties. In other words, if somebody scores high on this, the Beck Anxiety Inventory, we suspect they're probably also going to score high on the Penn State Worry Questionnaire, and vice versa. If somebody scores very poorly on the BAI, or I say very poorly, if they scored really low on that, which I guess would be a good thing, if they scored really low on the BAI, we would predict they would also score probably pretty low on the Penn State Worry Questionnaire. So the question is, if I know what somebody's BAI is, could I also then surmise or predict what their Penn State Worry Questionnaire is? Here's how we do that. So we are going to take in this information. Now, I give you more information than you need here. I'm saying there's 21 questions, a maximum score of 63. Really, you don't even need to pay attention to that stuff. What you need to know is the mean and the standard deviation. That's really the only important thing here. This other stuff might throw you off. So don't focus on it. Just focus on the mean and the standard deviation here. So let's give ourselves two questions, and we want to try to solve these two questions. So the first one, if we can assume that these two tests measure the same thing, which we do, we can predict that someone who gets a 20 on the BAI might get a blank on the PSWQ. So if we say that somebody here got a 20 on this test, what will they make for the Penn State Worry Questionnaire? The second question then is, if I score a 35 on both of those, is that unusual? So you might even be able to eyeball this second question right here, but you know, if we're dealing with mental health, if we're dealing with patient outcomes, we don't want to just eyeball the data. We actually want to know. So let's solve these two questions. So remember, what we want to do here is we want to calculate the z-score, which you will remember z is going to be equal to x minus mu divided by sigma. And then we want to apply this next piece, where we are going to try to find our predicted x by multiplying z by sigma and then adding mu, or the population mean, which is exactly what I show here. So if I'm applying this here, I'm going to go back and we're dealing with this first question, which is about if we have a 20 on the BAI, what will be the equivalent on the PSWQ. So let's look at the parameters here. We got a 20, the mean is 15, standard deviation is 5. That's where these numbers come from here, where we have the mean, so the x is 20, and then we have the mu, which is 15, over the standard deviation, which is 5. So when we plug that in, that gives me, it's going to give me 5 over 5, which is equal to 1, right? So what does that mean? Basically, if I scored a 20 on the BAI, I have a z-score of 1, which means that I scored 1 standard deviation above the mean, which is great. So if I want to apply that to the Penn State Worry Questionnaire, now I'm looking at this right here, right? So x is going to be equal to z times sigma plus mu. What values am I putting in there? I'm going to put in the Penn State values now. So the Penn State values are going to be 30 and 7. So 30 for the mu and 7 for sigma. So basically here, to find this new x, I'm going to plug in 1, because I got the z-score of 1 over here, 30 for the sigma, and 7 for the standard deviation. And so if I do that, that is going to give me 1 times 7 is 7, plus 30 is 37. So the answer to that first question is going to be 37. That if we scored 20 for our anxiety score, we would predict that they'd have a Penn State Worry Questionnaire score of 37. So a BAI score of 20 is like a Worry Questionnaire score of 37. Ooh, so here now let's make it a little bit tricky. Let's make it a little bit interesting. And by the way, you can almost certainly expect questions like this on the exam, which is why we'll do another example in the third video of something just like this. So if I score a 35 on both tests, would that be unusual? So the way that we need to do that is we're going to convert both of those scores to z-scores, a 35 for both tests, and then we're going to try to interpret those. So what I'm doing here is I'm throwing this into our BAI score here, and I'm going to do the same thing for the Penn State Worry Questionnaire. So walking through this, here's how I get these numbers. If I have a score of 35 on each that I can plug in for each of these, because I want to find the z-score for both, I'm going to find a 35 here and a 35 here. And then for mu, for BAI, the mu was 15, the standard deviation was 5. For the Penn State Worry Questionnaire, the mu was 30, and standard deviation is 7. Now when we plug all that in, this is what it looks like. 35 minus 15 is going to be 20 divided by 5, which is 4. For over here, we have 35 minus 30 is going to give us 5 divided by 7, which is 0.714. So, is this unusual? Yeah, we would say this is unusual. Why? How do we know it's unusual? Because what we're showing here is that one of these scores, the BAI, is much, much higher above average, right? Above the mean. That is 4 standard deviations above the mean. That seems like it might be an outlier. Over here on the Penn State Worry Questionnaire, this is actually not even 1 standard deviation above the mean, which means that it's a pretty standard score. It's not unusual at all. And so those things are unusual. That means that these two things must be unrelated, or it must mean that whoever responded over here, that this is an outlier piece of data, because this is a very radical score, one that's very unusual, and a very common score here. Here, I thought it might be kind of fun to kind of plug all these values in to kind of try to convert them, but I actually messed this up. And instead, and I'll tell you how I messed this up, that basically what I did is I plugged in 0.71, which is over here, and so I'm plugging this back into the formula that would give me the Penn State Worry Questionnaire, which is just a fancy way of checking my math. And so whenever we count for rounding errors, this goes back to a 35, right? But if I wanted to kind of fix this, and I wanted to try to figure out what would be for this, if I want to try to convert the BAI to the Penn State Worry Questionnaire, what I would do here is actually plug in 4 multiplied by 7 plus 30, like that, which would give us, so this would be, instead of this, actually let me erase that, that would give us 4 times 7, which is going to be 28, plus 30. So it does not give us this at all. Instead, it's going to give us 28 plus 30, which gives us a predicted observed value of 58, which is quite a bit higher than average. All right. And then again, I just want to kind of point out what this means is, you know, if we're thinking about that, the 60, 68, 95, 99 rule, that 4 standard deviations above the mean is way over here. So that is a very unusual extreme score for anxiety, whereas something that's like 0.71 z-score would be somewhere around here. So not that unusual. And that is all that I want to talk about for this chapter. I'm going to make one more video where we're going to go through a very similar example to show you, how to calculate these things so that we can get a little bit familiar and comfortable with it. And I will see you there. So, bye-bye, everybody.